All right, guys, we're gonna go ahead and get started on this Kahoot. Oh, Cream's gone. You can use I'll send it again, the link and the code anytime during the Kahoot to join in. You don't have to be there from the beginning to join in. Um, but I mean, ultimately, this is just for practice. So let's get started. What does an account lockout potentially indicate? Software update, normal login, brute force attempt, or printer error? Just press the corresponding color or shape to whatever answer you see on my screen, on your screen. Brute force attempt locks out the password from too many attempts. The account's getting locked out from the software update. That's probably not a good thing. Impossible travel login suggests what? Network latency, server downtime, VPN usage, credential compromise. Excellent. Spikes in network traffic off hours may indicate which of the following? Regular backup, CPU upgrade, data exfiltration, firewall update. Uh, Disabling antivirus update is an example of which of the following? Malware persistence, security optimization, patch management, user error. Also, Kareem, if you're having trouble with doing the Kahoot at the same time, you can feel free to just put your answers in the chat if you wanted to just guess and try. Yeah, this was persistent through disabling the antivirus to hide its presence. Logs being deleted unexpectedly can indicate which of the following? Hard drive replacement, attacker hiding presence, update installation, or system cleanup. Alright, attacker hiding their presence. Network segmentation primarily helps with which of the following? Reducing energy usage, limiting lateral movement, simplifying backups, speeding up internet. Excellent. ACLs define which of the following? VPN encryption type, OS update schedule, antivirus scan frequency, or who can communicate with what? It's okay. It happens. I know Kahoot can also be kind of weird, needing the two screens and stuff, so I figured that was just a misread there. Allow lists and applications do what? Restrict execution to approved software, block unknown software, encrypt files automatically, or disable firewalls. Awesome, Kareem. I know it's like I said, I know it can be a little weird to get the hang of at first, but you'll see the answers and stuff on my screen, and then you'll click either the color or the shape that you want to answer on your screen. All right, that's doing great. Strong password policies and least privilege are part of which of the following? Network segmentation, encryption, operating system hardening, or backup strategy. Encryption is just hiding the information through ciphertext and algorithms. You're hardening your OS by strengthening your password policies and who can do what. Two creams. Host-based firewalls and IPS are used to do which of the following? Track login times, manage user roles, monitor and control traffic on endpoints, or backup files. So an employee logs in from New York at 9 a.m. and London at 10 a.m. What is likely happening? VPN misconfiguration, credential compromise, routine audit, or normal behavior? Fifteen seconds left. Excellent. Workstation suddenly stops receiving antivirus updates and can't access the security sites. What's most likely the cause? Malware attempting to maintain persistence. User disabled updates by mistake, expired software license, or network outage. Fantastic. Keep it up. Almost done. A critical database is isolated from other systems. Why? Easier backup, speed optimization, cost reduction, or regulatory compliance and reduced exposure. Yeah, isolate it because you got to keep your stuff safe and reduce the exposure if someone breaks in to your server and your critical database is segmented off, then the attacker can't get to it, at least not as easily. Anything to make it harder. Unused software is removed from a workstation. This is an example of which of the following? System hardening, malware installation, firewall misconfiguration, or network segmentation. Excellent. And last but not least, an app refuses to run unless its hash matches the trusted list. What is this? OS permission error, firewall block, application allow list, or user misconfiguration. Excellent. Great job, guys. I know you were having some difficulties there, Kareem, but I can send you this Kahoot later so you can do it on your own if you'd like. All of these are public, and I'm happy to give them out so you guys can test yourself on any subjects that you've missed or you want extra practice with. That being done, unless anybody has any questions, we're going to move on to hardening techniques. Got a few videos, but they're on the longer end today, so I don't know how many we're going to get through. Of course. Here, I can send you the link. How's it going, Sunny Don?
Hello, good evening.
Anthony, any good sources for performance-based questions? I use ChatGPT to quiz me a lot. I know the community has a lot of resources. Send that to you real quick. Gladys went to people who have certifications and got a bunch of materials for the different certifications here. Yeah, there's a whole bunch here. There, if you go there, you should find a whole list of resources for a bunch of different certifications there that people have given out. If you find other ones that aren't listed there, feel free to just send them over, and we can add them. I know. How are you doing, Sandy Down? I know someone that had some good PBQ practice, though. I'll get that from him because that's something I've been meaning to do for these sessions, anyways. We already did one session at week 11 that was the full 90 question Kahoot as practice, and I'd like to do one that has performance based practice because that one's, as everyone knows, very important. And Sunny Dawn, I can send you the Kahoot we did just now. You came in just as we finished it.
Okay, that's fine. Okay, that's fine.
All right. We're going to get started with these videos. If anybody has any questions, just type in the chat or say something in your mic. Either way is fine. But we'll get started with hardening techniques.
If you take a look around your network, your servers, and other devices, you may find opportunities to make those devices just a little bit more secure. And in this video, we'll go through a number of hardening techniques. Let's start with a server. The system hardening refers to the operating system that's running on this server. Operating systems like Windows, Linux, macOS, and others are very different, but there are some best practices to ensure that these operating systems remain secure. One of the first most significant steps for keeping these systems hardened is to always apply the security updates. These would be updates to the operating system and security patches that are usually included with those. Manufacturers like Microsoft will release these patches every month, and other manufacturers follow a similar schedule. You should also make sure that the user accounts on these systems are well secured. One of the ways to do that is with a password policy. You could set a rule that says that there should be a certain minimum password length and there should be a certain complexity associated with those passwords. For example, your password should be at least 8 characters long, and the password itself should include uppercase characters, lowercase characters, numbers, and special characters.
The reason we exist is because you cannot stay ahead of all threats. So what we do is we block.
Another good idea is to have limited access for these accounts. Not every account on the system should be an administrator, and each individual user account should only have the rights and permissions necessary for that user to do their job. If you're accessing this device across the network, it's also a good best practice to limit who may have access to this particular system. You might include an IP address range that's permitted to access this server, and if someone tries to access this server from a different IP address, they would be denied access. And of course, it's always good to monitor and secure the system with antivirus, anti-malware, or some other type of endpoint detection. Another good hardening technique is to encrypt any data that you would like to protect on these systems. One way to do this is with the file system itself. You can select individual files or folders and tell the operating system to only encrypt that specific data. This is easily done using things like the Windows Encrypting File System, or EFS. If you would like to secure the entire drive with operating system, user documents, and anything else that's stored on this system, you might want to use FDE, or full disk encryption. This does encrypt everything that is stored on a particular volume, and you can do this with built-in tools like Windows BitLocker or the File Vault utility in macOS. And if you're communicating between devices across the network, you might also encrypt all of your network traffic. This can be done using a virtual private networking option, or VPN, and the applications that you're using may have encryption built into those applications already. For example, if you're connecting to other devices from your browser, you're probably using HTTPS on that address bar, and that encrypts all of the data between that browser and the web server. It's common these days for people to have 2, 3, or even more devices that they might use throughout the day. And we also need to think about how to harden each of these individual user endpoints. We're of course concerned about attacks that may be inbound to any of these devices. There could be someone on the internet trying to access those devices directly. If a device does become infected with malware, it's possible that that malware may try to attack other systems using the user workstation as the starting point. We need to think about the type of security that we might put on a desktop computer, a laptop computer, or even the mobile tablets or mobile phones. All of these are probably running different operating systems, using different applications, and we need to apply the proper security for each individual platform. And of course, there's never one single option or button to push to enable or disable security. You need to use many different types of security tools and utilities, and all of those work together to provide defense in depth. It's estimated that there are over 1 million malware variants created every day. To address this scalability problem, the industry is focusing on the next generation of malware detection through an EDR. This stands for Endpoint Detection and Response. EDR can certainly recognize known malware and vulnerabilities based on a signature, but it goes beyond signatures to provide additional security. For example, the EDR could use behavioral analysis, watching what the user does, watching what the applications do, and identifying when something malicious may be occurring, even though it may not have a signature for that particular piece of malware. EDR might also include machine learning for rapid identification of malware and malicious software, and process monitoring can constantly watch all of the processes running on your system, and if a new process suddenly began on your system, EDR can recognize that process and begin monitoring it for any type of malicious activity. EDR also has the ability to go much further than a traditional antivirus or anti-malware application. For example, the EDR itself can perform root cause analysis on the threats that it's seeing. Once EDR recognizes something that could be malicious, it begins performing additional studies on what that particular process might be. And after doing some research, it can make a decision on whether that is something that is malicious or something that should be allowed. And once malicious code is recognized, the EDR itself can immediately take action. You don't need to wait for a technician or a help desk ticket to be created. Instead, EDR will isolate this system, quarantine that threat, and even roll back to a previous config to remove that virus from the system. This entire process can be automated through the use of an application programming interface, or API. So the EDR can perform all of its functions autonomously and then report all of that information back to a central management console. It's very common these days to have a host-based firewall running on your operating system. This is a software-based firewall that runs behind the scenes, and it provides a way to allow or disallow certain traffic flows both inbound and outbound from your system. Since the software-based firewall is sitting on your operating system itself, it gets to see all of the data before or after encryption has occurred. So it has complete visibility to what might be going on, and it can decide which processes should be allowed to communicate on the network and which processes should be blocked. This is also a great place to monitor for unknown processes that may have been launched because of malware or some type of security vulnerability. And if the host-based firewall sees something unusual, it can be configured to automatically block that traffic until administratively approved by the user. This software-based firewall is running on each individual system, but it can be managed from one central console. It's very common to look for known attack types on the network by running an intrusion prevention system, but there are also host-based intrusion prevention systems that can provide this type of security on each individual device. This is often built into your EDR or your anti-malware software, and it watches all of the traffic that is inbound to your system to look for anything that might be a known vulnerability. The host-based IPS or HIPS can also secure application configurations and operating system configs, and it could look for and verify any inbound updates for securing that system. We commonly associate intrusion prevention with looking for some type of malicious action. So this might be something based on signatures that are stored in the IPS. It might be based on heuristics or behavioral changes. Since the IPS is on the operating system itself, it can extend this visibility into the way the operating system is working. For example, if the host-based IPS recognizes a buffer overflow or registry change, or perhaps some files were modified in the core Windows operating system folder, it can send an alert and block that particular process from continuing. Each time you install an outward-facing service on a server or workstation, ports are opened inside of the operating system, and those ports can be accessed across the network. Ideally, you should close as many of these ports as possible. Each one of those ports is an opportunity for an attacker to find a vulnerability that would allow them to gain access to that system. This control of open ports can certainly be done on the server or workstation itself. You can also install a firewall to provide this port-based protection. Ideally, you could even use a next-generation firewall to provide much more granularity of not just the port number, but the service that's using that port number. Sometimes these ports are opened without the knowledge of the end user. When you initially install an operating system or you install additional applications onto that operating system, you could be unknowingly opening ports in that system. And there are cases that I've documented that show an application manufacturer saying that you can install this application, but once this application is installed, you need to open port 0 through 65,535. This would effectively open every port on that particular server, which would certainly not be the best practice for a secure system. If you see an example like this for software that you're installing, it's not because the software needs to have all of these ports open, but they'd rather not be called if there happens to be an issue communicating across the network to the port number used by the application. And if you're not sure which ports are open and which ports are closed on your system, you can run a scan. Nmap is a great tool for scanning available port numbers on a system, and after a few minutes, it can give you a great deal of information about exactly what ports might be open on an individual system.
Did you know you can AFK Bloods and Zaya whilst learning to code in Python? Go to boot.dev.
If you install a router, a switch, a firewall, an access point, or almost any other device, there will be a default configuration screen that allows you to set the settings in that device. These management interfaces might also be found in applications that you've installed on a system, and all of these might contain very sensitive data and certainly information that would be interesting to an attacker. Normally, when you would first log in to one of these management consoles, it will prompt you to change the password. But not all systems provide that prompt. So it's important that you manually go into these devices and change the default configuration. The attackers can very easily find what the default settings are for a username and password, and you want to be sure that all of your systems are secured against that type of attack. And in some cases, you can configure multi-factor authentication or perhaps centralized authentication that synchronizes with all the accounts in your network. Every piece of software that you use on a system has some type of bug inside of it. This may not be a bug that you found yet, but eventually you may find something that is a security vulnerability built into this software. And of course, you may have installed tens or hundreds of different applications on your system, and each one of those applications probably has a different process for performing security updates. This makes it very challenging to keep these applications up to date and secure because you would have to go into every single application with their unique update process to ensure that everything is always running the latest version. Instead, the best practice might be to delete any applications that you're no longer using. This would certainly remove any security concerns, and if you're not using the application anyway, you certainly don't need to have it loaded on that system. This is a relatively easy fix, and it allows you to remove one more application from the list of keeping everything up to date on your system.
How does everyone feel about that? Any questions on any of that? Fairly straightforward. It's all stuff we've covered for the most part, but definitely just as vital. All right. If we have no questions, we will move on to cloud infrastructure. Please post any questions in the chat that you have, or stop me at any time.
At this point in the evolution of cloud technologies, it's very likely that you or your organization has one or many applications running in the cloud. These could be running as infrastructure as a service, platform as a service, software as a service, or one of the many other types of services available in cloud-based infrastructures. But in all of these cases, the question still remains, who is responsible for the security for all of these different cloud-based systems? Fortunately, if you're working with a public cloud provider, they are probably going to provide you with a matrix of responsibilities. This will clearly show who's responsible for the different aspects of the technologies running in the cloud. Not all cloud providers provide the same matrix. There may be differences depending on the cloud provider that you're using. And you might have a contract with a cloud provider that modifies the default matrix of responsibilities to better fit the needs of that contract. This is a responsibility matrix that was taken from a large cloud provider. You can see that it's broken up by software as a service, platform as a service, infrastructure as a service, and on-prem or on-premises. Anything in blue is managed by the customer, and anything in yellow is managed by the cloud provider. In some cases, there's an overlap where both the customer and the provider are responsible for everything at that level. So for this cloud provider, if you're wondering who's responsible for the operating system, if this is software as a service, it's the provider, platform as a service is the provider, and infrastructure as a service, and obviously on-premises would be the responsibility of the customer. You can compare that with a section of the matrix for accounts and identities. That would obviously have a significant security concern, and in the case of this cloud provider, the customer is always responsible for anything associated with their accounts. If you're wondering what the responsibility matrix might be for your cloud provider, they probably already have it documented as part of their services. In some organizations, one cloud isn't enough. You may have multiple clouds that you're using across different cloud providers. We refer to this as a hybrid cloud, and although it adds additional flexibility when you're using different cloud providers, it also includes an extra level of complexity when you're needing to manage across those providers. For example, most cloud providers don't talk to each other directly, and in fact, many of the systems between different cloud providers may work in very different ways. So you might have to manually configure all of your settings separately for each cloud provider. For example, you might have authentication that needs to occur, and if you're configuring it differently on each provider, you may have a mismatch between one provider and another. Or you may be configuring server configurations or firewall settings, and all of those need to match between all of these different providers. And since they're not connected to each other, it's an opportunity to have a mismatch between one and the other. It can also be difficult to manage security and other logs between these different providers. Each provider writes a different type of log with different terminology, and it may be difficult to combine those together to see what's going on. And in order to take advantage of this hybrid cloud, it may be perfectly normal for data to constantly be transferred from one cloud provider to the other. Each time this data is sent from one provider to another, it's traversing the public internet. So you have to make sure that all of your security settings are configured to protect that data in transit. When working with the cloud, you're most likely working with a cloud provider, but there are also third parties for applications and other cloud-based devices that you also have to manage. For example, you might have an application you've written in-house and you've posted that application to the cloud, but you would like to put a firewall in front of that application to provide additional security. You're most likely using a firewall from a third party to provide that security. A good best practice is to have a vendor risk management policy so that you can manage and maintain the security for these third-party technologies. We also have to think about how we'll handle incident response for all of these third-party products and technologies. We certainly have our own internal processes, and we have the processes associated with the cloud provider, but we also have to bring in all of these other third parties to participate in this incident response process. And of course, we need to constantly monitor these third-party processes and devices. We want to be sure that the security of these systems and the availability is always working as expected for these cloud-based systems. Cloud-based infrastructures almost always require some type of infrastructure as code. This is a way to describe an application instance or a portion of the infrastructure in the cloud, but you're defining it as code rather than defining it as a particular piece of hardware. For example, your infrastructure as code may define what hosts need to be built, the type of web servers that are running on these hosts, and database servers that would also be used for this infrastructure. This allows you to easily build out an infrastructure, and it also allows you to easily modify the infrastructure so that you can change the configuration as needed. You can build this out in the code itself, so the next time this code is used to build out the infrastructure, it takes all of your changes into account. Now that you've created a perfect version of the application instance, you can easily use that code to rebuild the instance on any cloud provider at any time. This is one of the significant benefits of cloud computing, is that you're able to create an entire infrastructure all based around one single definition of infrastructure as code. When we build out an application instance in the cloud, we often refer to different servers. But what if we could build an application instance that had no servers? This is referred to as a serverless architecture. Instead of simply accessing a single application, we are instead accessing individual functions that are handled by that application. Each function handles a small piece of the application, and anytime we need to perform one of these functions, we address that part of the serverless architecture. What's also interesting in this serverless architecture is there's much less emphasis on the operating system itself. Each one of these smaller application functions can run in whatever operating system happens to be appropriate at that particular time. From the application's perspective, we're only interested in sending and receiving information for that small piece of those autonomous functions. We don't have to worry so much about what operating system is running underneath. Your application developer is going to spend time breaking the application into these smaller functions and then deploying them on the server side. This also means that you would only need to run these particular application functions when they're needed. This also saves time and money, especially on a public cloud-based infrastructure. If the application needs to access a particular function, it can be built in real time in the cloud. That function can then be referenced for the application. And if it's no longer necessary to continue to run that compute container, it can then be removed from the cloud until you need it the next time. Most of the work that's happening with a serverless architecture occurs in the cloud. So the bulk of the security associated with this application instance and the serverless architecture is all in the cloud itself. Cloud infrastructures also allow us to have extremely efficient application instances. Traditionally, we've used monolithic applications running on our desktops. We would install large applications onto our storage drives. We run all of those applications in the memory of our system, and that one big application handles all functions you need for that app. Everything about that application is running as one single executable. The user interface, the login screens, all of the business logic that you would have inside of that application all occurs on the client of that monolithic architecture. This also means that you have a large application that needs to be installed on one local machine. And if that application needs to be updated, we need to process a change control. We need to send the changes down to that particular device. It needs to be installed on that machine. And then we are able to use the newest version. In the cloud, we have the opportunity to use a more streamlined process that focuses on a microservice architecture. We're able to take advantage of microservices by using APIs. These are application programming interfaces, and it allows us to programmatically control the way that an application is working. So instead of having one single executable that handles everything for the application, you can break out individual services for the application and run them as separate instances in the cloud. All you would need to do as the client is talk to the API gateway, which would then send the request to the appropriate microservice. This greatly extends the scalability of the application. If there's a certain portion of the application that is being used more than others, you can roll out additional microservices to handle that load. This also makes it more resilient. If you happen to lose a particular microservice, the rest of the application will continue to work. And since the security is based on the microservice that's running, you can provide the proper amount of security based on the service that happens to be running. If the microservice is handling authentication, there will be a set of security processes for that. And if this microservice is reading or writing information to a database, there will be a security process associated with that microservice.
All right. I know that one was a lot to take in. How are we feeling about that? All right. Well, if we have no questions, then we have one more video I can fit into our session today. Network infrastructure concepts. Once again, please stop me if you guys have any questions. Post in the chat or say something in the mic. Otherwise, we'll get started.
One concern in networking is that it might be possible for an attacker to move from one device to another using some type of connection that previously exists. But what if you're able to isolate the devices physically? You might, for instance, have switch A and switch B, and in this scenario, we've created an air gap between both of those devices. If an attacker does find a way to get access to switch A, they would have no way to gain access also to switch B. If there is a requirement for devices on switch A to talk to devices on switch B, then there would obviously need to be some type of connectivity. This might be a direct connection, or you might be passing the data through another switch or a router. This air gap can be configured for a number of different scenarios. For example, you might have all web servers in one rack and all database servers in another rack. And if you have an air gap in place, this physical isolation prevents either of those from communicating with the other. You might also see this in a managed service provider where there are many customers being managed by that single company. And for highly secure environments, the managed service provider might use this physical isolation to put one customer on one switch and another customer on a completely separate, physically isolated switch. Here's what this might look like. We have customer A on one switch and customer B on the other switch. Devices plugged into customer A switch can communicate between each other, and devices plugged into customer B switch can also communicate to each other, but notice there's no connectivity between customer A and customer B. Of course, with physical isolation, we also need two separate physical switches. And if you have 100 customers, you would need 100 switches. Obviously, this is not going to scale very well. But there are technologies built into your switches that allow for segmentation, but still have everyone connected to the same physical switch. This is using VLANs, or virtual local area networks. This allows you to configure certain interfaces on your switch as belonging to one VLAN and other interfaces on the switch as belonging to the other VLAN. VLANs cannot communicate to each other directly, so this has the same effect as having two separate physical switches. This would obviously simplify the network design, and you would need fewer switches to accomplish the same amount of segmentation. When we think about switching and routing, we often consider the physical aspects of those devices. There's interfaces we would connect to, there's a power connection, and we would send information through those devices to be able to forward traffic from one device to another. But inside those devices, there are different operations that are occurring all at the same time. We refer to these as planes of operation. And from the perspective of SDN, or software-defined networking, there are three separate planes that we'll focus on. One is the data plane, the other is the control plane, and then there is the management plane. This allows us to break these devices apart into their individual functions. And when you do that, you can begin coding that as software. This is a way to take the physical world, turn it into software that can then be used in our cloud-based world. The infrastructure layer, or the data plane, is the part of the device doing the hard work. Whenever we think about switching and routing, we're talking about the process of forwarding traffic from one device to another, and that forwarding process is what's happening in the data plane. This is also where network address translation occurs, any type of encryption, trunking, or anything else relating to the networking part of forwarding data. All of this data that's being transferred from one device to another is being managed by the control plane. For example, if you're using a router to forward traffic between IP subnets, there needs to be some type of routing table inside of the router so that we know where this traffic should go. And in that scenario, the control plane is responsible for managing the routing tables and then taking action on where this data should go. This also includes any type of dynamic routing updates, network address tables, or anything else that can tell the data plane how to get data from point A to point B. And of course, at some point, you'll need to make configuration changes to this device. When you're connecting to a switch at the command line through SSH and you're making configuration changes, all of those changes are occurring in the management plane. Those changes would then dictate how the control plane manages its session tables and routing tables, and ultimately that determines how the data plane is going to forward traffic. If we look at a physical switch, we can almost pull apart where the different planes of operation exist. For example, on the front of the switch, we have a number of interfaces that we're connecting our devices to. This would be the data plane, because this is what's sending information from one device to another. The control plane handles the lookup tables and address translations that are necessary for the data plane to operate. And obviously, we'll need to connect to this device over a console or management interface, and that all occurs at the management plane. Now we can take these three planes of operation and turn them into more of a block diagram. Here's exactly the same switch, but now we're only dealing with the data plane, control plane, and management plane in more of a block diagram. We know that our network traffic flows on the data plane of this device. We have a control of that traffic occurring in the control plane, so things like dynamic routing protocols and static routes. And the configuration of this device occurs at the management plane using SSH, SNMP, or application programming interfaces. This has allowed us to create software versions of these physical devices that we traditionally have used so that we can now use these devices in the cloud. Here's a common cloud-based configuration. We have an internet connection that's connecting to a load balancer, and that load balancer is connecting to web server A, web server B, and the database server for this application. With cloud technologies using SDN, we can now immediately build out infrastructure devices we might need. For example, in this scenario, we might want to add some firewalls. So we can add a firewall that would separate the internet from the load balancer. We might want another firewall to separate and control traffic between the web servers and the database server. We're able to click a button and dynamically create this technology in the cloud thanks to our software-defined networking.
All right. Some more important stuff there. I know it's a lot to take in. So, like I said in the chat, I'll be posting a recording with a write-up and notes and links and everything like that. Does anybody have any questions before we finish up for today? All right. Well, if there are no questions, then I'm going to stop recording here.